This brings us to an interesting dilemma. I have stressed several times that one of the big advantages that the Cardano EUTXO model has over something like Ethereum is the fact that validation can happen in the wallet. So as I explained before, transactions can still fail because a transaction can consume an input that when the transaction arrives on the blockchain at the node for validation has already been consumed by somebody else. But in that case, the transaction simply fails without having to pay fees. But what can never happen or should never happen under normal circumstances is that a validation script runs and then fails, because you can always run the script under exactly the same conditions in the wallet already. So you see that it would fail before you ever submit it. And that is very important and a very nice feature. But if you think about it, it's not clear how to manage time in that context. Because time is obviously important, because we want to be able to express validation logic that says that a certain transaction is only valid after a certain time has been reached or before a certain time has been reached. We saw an example of that in the very first example, the auction example, where bids are only allowed until the deadline has been reached, and the close endpoint can only be called after the deadline has passed. And if you think about that, that seems to be a contradiction, because time is obviously flowing. So when you try to validate a transaction that you're constructing in your wallet, the time that you do that in the wallet can of course be different to the time that the transaction arrives at a node for validation. So it's not clear how to bring these two together to, on the one hand, handle time, but on the other hand, guarantee that validation is deterministic, in the sense that if and only if it succeeds in the wallet, it will also succeed in the node. And the way Cardano solves that is by adding this Posix time range field, txinfo valid range field, to a transaction. And what that specifies, so it's we will look at that type in detail in a moment, but basically it gives a valid time interval. It is a time interval. So it says this transaction is valid between this and that time. And that is specified in the transaction. And now when a transaction gets sent to the blockchain, submitted to the blockchain, and validated by a node, then before any scripts are run, some general checks are done. For example, that all the inputs are present and that the balances add up and so on, that the fees are included. And one of those checks that happens before validation is that the time range is checked. So when a node is validating, one of these pre-checks before validation is the node checks the current time and compares it to the time range specified in the transaction. And if the current time does not fall into this time range, then validation fails immediately without ever running the validator scripts. But that also means that if these pre-checks succeed, then we can assume that the current time does fall into this interval. And then validation is completely deterministic again. This is just a static piece of data attached to the transaction. So the result of validation does not depend on when it is run, whether it's run in the wallet before submission or in one of the nodes when validating a transaction. And this makes it possible to resolve this apparent contradiction between having deterministic validation on the one hand and taking time into account on the other hand. So the trick is to do the time check before validation is run. And then during the execution of the validator scripts, we don't have to worry about it anymore, and we can just assume that the current time falls into this interval. Because if it wouldn't, then validation wouldn't even run in the first place, because then validation of the transaction would have failed before. By default, all transactions use the infinite time range that starts at the beginning of time or at the genesis block and lasts for all eternity. So such transactions will always be valid, no matter at what time they arrive at a node for validation. The only exceptions we have seen so far were those in the auction example, because the bid and the close couldn't use the infinite interval because we made sure that the bid happens before the deadline and the close after the deadline. But by default, all transactions, including those that you send from Daedalus, for example, always use the infinite time range. There's one slight complication with this, and that is that Ouroboros itself, the consensus protocol powering Cardano, doesn't use Posix time, it uses slots. So it counts slots, and each slot, this lottery happens where a slot leader is determined and that slot leader can produce a block and so on. So slot is the native measure of time on Cardano. But Plutus uses real time. So somehow this has to be converted. So we need to be able to convert back and forth between real time and slots. And this is no problem as long as the slot length is fixed. Right now it is 1 second. So right now it's easy to go back and forth between real time and slot numbers. But this could change in future. So there could be a hard fork, some parameter change that would change the slot time. And of course, we can't know that in advance. That may be a decision that is made years in the future. So we don't know right now what the slot length will be in 10 years, for example. And that means that slot intervals specified at transactions mustn't have a definite upper bound that is too far in the future. It must only be as far in the future as it is possible to know what the slot length will be. And that happens to be something like 36 hours. We know what the slot length will be in the next 36 hours. Because if there's a hard fork, if there's a change in protocol parameters, then we know that at least 36 hours in advance. So that is something to keep in mind. You can't specify arbitrary time ranges there in the transaction interval. It must only be at most 36 hours in the future, or it can be indefinite. So for all eternity, that's also fine. But if it's a fixed time, like the deadline in our auction example, when we submit the transaction, the deadline basically mustn't be further than 36 hours in the future when we submit that. Or the deadline could be, but then we mustn't specify the deadline as upper bound, but some other time that lies before the deadline. It is at most 36 hours in the future. So that's a slight complication that arises from the fact that Plutus uses a different concept of time than Ouroboros itself. Of course, it's more convenient to use real time, especially for real-world contracts where you might want to specify deadlines in real-time dates, for example. But in order to translate back and forth between time and slots, you have to be a bit careful when you submit transactions, when you construct transactions and set the slot interval or the time range. So let's look at this Posix time range type. And we see it's defined in model plutus.v1.ledger.time. And it's just a type synonym for interval Posix time. So let's look at the interval type. We see interval type that takes one type parameter, and we see it's specified by a lower bound and an upper bound. We can drill into those types as well. So in lower bound has one constructor lower bound and then an extended A and closure. Let's first look at closure. That's just another name for bool, and it specifies whether that boundary is included in the interval or not. And let's look at this extended. So this extended can just be an A, the finite constructor, or it can be negative infinity or positive infinity. Now if we scroll down here, we see there are a couple of convenience functions. So member, for example, allows us to check whether a given A is included in interval A. provided A has the odd constraint, is an instance of the odd class, which means that you can compare two A's, whether one is less than or greater than or equal to the other. So Posix time, for example, is an instance of odd, as are slots. Interval is a smart constructor for intervals that just gives us an interval with these two A's as lower and upper bound included. Then we have from and to construct an interval that starts at A and lasts until eternity, and to the opposite, an interval that stops at A. Then always is the interval that is used by default, that includes all times. Never is the empty interval. Singleton is an interval that only contains this one A. Hull is the smallest interval that contains the two given intervals. Intersection, as the name suggests, intersects two intervals. The result will again be an interval. Overlaps checks whether two intervals have an element in common. Contains checks whether one interval is contained in the other. So we must just check which way around. So I think the second one must be included in the first one. Is empty, checks whether an interval is empty. Before checks whether the given time is before everything in this interval. After the opposite, whether the given time is after everything in this interval. These are just convenience functions to construct strict lower and upper bounds. We can play with intervals a bit. So let's start a REPL. And let's import Plutus v1 ledger interval. Now, for example, we can use this interval smart constructor. And as A, let's just use integers for simplicity. So for example, the interval between 10 and 20. We see, okay, it says the lower bound is finite 10. 10 is included. The upper bound is finite 20. 20 is included. So for example, we can now check with member whether 9 is a member of this interval. It's not, but 10 should be. It is. So should be 12 and 20, but 21 shouldn't. Or let's use the from. So we have from 30. 21 is not included in that. 30 should be. And now everything larger than 30 should also be. Right, and 2. Let's try the 2. So 31 still shouldn't be included. 30 should be. And everything lower than 30 as well. Okay, so that seems to work. Let's try one more thing, maybe the intersection. So let's intersect this one from 10 to 20 with the one from, I don't know, 18 to 30. And as expected, we get the interval from 18 to 20. Let's also try the contains and the overlap. So for example, contains to 100, interval 30, 80, true. So what does that mean? That means the interval that starts at 30 and ends at 80 is contained, fully contained in the interval that starts at the beginning of time and goes to 100. If we now change this 80 to 100, it should still be true, but if we change it to 101, it's no longer true. But if we check overlaps, then it is true, because, for example, 40 is contained in this interval and also in that one. So overlaps is true, but contains is false because this second interval is not fully contained in the first one. The 101 is in the second one, but not in the first one. If we, however, use something like 101 to 110, then it's false, then they don't overlap any longer. So now let's look at an example for using this time range.